Right, so the next talk is Proqueries and Praqueries.
All right, so we've seen querying, algebraic theories, profunctors. So now we get to put them all together in this talk. So it's really nice how that all lined up. So today I'm going to talk about some work in progress in categorical database theory. This work expands the algebraic model of categorical database theory developed in these two papers, Algebraic Databases and Algebraic Data Integration. So some of the main results are that we introduce these things called proqueries, non-strict proqueries, and these are data transformations that are reminiscent of conjunctive queries. We prove correctness of proquery presentation composition, so that's what Gabriel was talking about. And we're going to introduce proqueries, which are data transformations similar to unions of conjunctive queries in relational database theory, and prove also correctness of their composition. So here's the story of categorical database theory. I'm not going to go through all of this, but it kind of goes back a little, for me, it was surprising how far it went back, the overlap of category theory and database theory. And then there's like a ton of work here on the sketch data model, but I didn't include all of that. And here's kind of like the modern iteration of it. And we're just going to focus on these two papers. So we already saw a bunch about this, so I get to go through it really quickly. Database schemas, small categories, database instances, capriciates, category presentations. Only thing different here is that I use dep instead of worksin. I have a different equation, but basically the same examples: sorts, equations, function symbols. This is the semantics of category presentation, provable equality relation. We've all seen this now. Here's the semantics. Here we actually end up with
I'm worried about 44 slides, but now
yeah, no, you shouldn't be worried. I'll just skip the whole talk at this point. So morphism of category presentations as before, but again, let me just reiterate that we take equations, which is a finite amount of data here, and then we need to prove their equivalent. So they don't have to be taken to actual equations. Now, instance presentations, as we saw, are category presentations with this extra bit here. And we think of these arrows here as generators. So this instance presentation has two generators and it has an extra equation here. And we write it like this. And we can display it as a table. So here we have 4 employees, E, E's manager, D, the secretary of the department D, the manager of that secretary. And what's interesting here is that this is very similar to what is known in relational database theory as incomplete databases. Incomplete information, also called labeled null. So given an instance presentation, we obtain semantics in basically the same way. We already saw this. Note, however, that there's no actual data here, right? So this is just keeping track of primary keys and foreign keys. So these are just kind of sets, okay? But in real life, we want more than just sets. We want to add in data. And so that was one of the ideas behind the algebraic data model. So here's the algebraic data model. So now algebraic theories. So an algebraic signature consists of sorts and function symbols, kind of like category presentations, but now function symbols are allowed to have higher array, so they can have more inputs. And we call the zero array function symbols constant symbols. So the algebraic signature for groups has one sort, G, and it has function symbols, M, which is multiplication, E, which is the unit, and I, which is inverse. And you can visualize these. And when you put together these function symbols, we call those terms, okay? And we'll use this notation to represent these, which I know might offend you guys because you love string diagrams, but so much. But here, these are like 3 variables, okay? So you imagine the free variables coming in there. And so some terminology, the whole thing here is the term, the free variables we call the context, and the domain is, the codomain is called its sort. So an algebraic presentation consists of an algebraic signature and a set of equations between terms. So here's the algebraic presentation of groups, and we add in these equations. Now, if I have an algebraic presentation, we can also define another equivalence relation, provable equality, we'll call it that again, on terms rather than just paths. And we get a semantic category. So the function symbols produce morphisms. And now when I have the higher arity, we think of that as product. And morphisms of algebraic presentations send sorts to sorts, function symbols to terms. And instead of setting equations on the nose, we again do it up to provable equality. And so what we'll get is a functor from algebraic presentations to finite product categories. So now for the rest of this talk, let's fix an algebraic presentation that we're going to call the type side. And we want to think of this as the kind of stuff you would see in SQL. Okay, so maybe we want strings and we want integers and we want some operations. So we have plus, successor, zero, taking two strings and concatenating them, and then all the letters as constants. And imagine there's like a whole bunch of other stuff that you might want. And we're going to use this to define an algebraic schema presentation. So an algebraic schema presentation U over a fixed type side consists of this stuff that we already saw. We're going to call, like we have a category presentation here. We're going to call those objects entities. We're going to call the morphisms there. They have to be unary on this side, foreign keys. And then we're going to have equations between them. These are the same equations from before. I just now use a different notation. Okay. And we're also going to have the type side here on the right. So you imagine that there's like a whole bunch of different stuff here, and also its equations that I haven't written down. But now we also have attributes, and these are going from the category presentation to the algebraic presentation, okay, in one direction. So here's the salary of the employee, here's the name of employees, the name of departments, and these we think of as actual data. Okay, and then we also have equations that involve these attributes. So here this is saying that the salary of the manager of this employee is 100 plus the salary of the employee, which is a sad fact of life. So we're typically not going to denote all of the operations on the type side. It gets a little messy. So this is what we'll think of as an algebraic schema presentation. So we want to talk about the semantics that reflect this structure. So given two categories, a bipartite category here consists of another category E equipped with a functor to the category with two objects and one non-identity morphism going between them. So 0 to 1, there's one morphism, and then the fibers should be C and D. So this is a profunctor, but let's not confuse that with how Gabriel was thinking of a profunctor. Just think of this as like two categories with a bridge between them. Okay, so if you use a schema presentation, then we actually obtain a bipartite category. So the left side we call the entity category, and the right side we call the type side. And this inspires the definition. So given a fixed finite product category, which I'll still think of as the type side, a schema is a bipartite category such that the inclusion from the type side preserves finite products. Now an instance is just a functor, the set that preserves the finite products of the type side. So I don't care about products or anything on the entity side, but I do care about the products on the type side. And we can define schema presentations and instance presentations just as we did before. And this allows us to input schemas and presentations into a computer. So in the algebraic model, instances can now display data other than labeled nulls, while still having incomplete information. So here, I'm going to give you a presentation for this database. Okay, so I have 3 generators of employees and I have 2 generators of departments. And now the actual data that's going to come here is given by equations. Okay, so this employee E0, her name is Alice, and then we have the name Bob and Charlie. Okay, and 2 departments, computer science and math. And these equations tell us who's everybody's manager is. So we see that Alice is her own manager, Bob's manager is Charlie, and Charlie is his own manager. But notice here that we don't know Bob's salary, and we also don't know Charlie's salary, but we do know Alice's salary. Okay, so we see that we have a mix of information, of data, and incomplete information. Now, if we really want to call ourselves database theorists, we need to be able to query our data. And this is where profunctors come in, which Gabriel talked about. Now, we can't just naively use profunctors because now we have this kind of algebraic aspect to it. So the idea of proqueries is simply what's the correct notion of profunctors between algebraic schemas. Okay, so if I have a schema U and I have an object in U, I'm going to let Y of U denote the following U instance, which is just given by on. So it's the representable instance on U. And we can present this super easily with just a generator and no equations. So suppose I have 2 schemas U and V. A strict proquery is a functor from U op to V instances. I should have said morphisms of instances are just natural transformations. And I require that if I input a type, that I get a representable instance. So I can put in an entity or I can put in a type and I get an instance, and every time I put in a type, I get a representable. In general, we want to allow proqueries to only be isomorphic, but every proquery is actually isomorphic to a strict one, so let's not worry about that right now. So we're only going to consider strict proqueries. So this is the analog of thinking of profunctors as COP indexed family of Proqueries sheets. But this extra twist comes in now because we're talking about attributes. Okay, but let's just look at an example here. So suppose I want to do the following thing. I want to select from my favorite example here. I want to select the name and the salary of all the employees who are their own manager, and I want to add 50 to their salary. I'm giving them a promotion. Maybe they're promoting themselves. So I can write this in select from where notation. So I want to select the name and the salary plus 50. So this is a perfectly good term. And I want to call that name new name and the new salary new sal. And so all I need is one generator E, and I want E to be their own manager. Okay, so here's the schema that I'm querying. So what I do is I create a new schema over here, and for every select clause here, I'm going to have a new attribute here. So here's new name and new salary. And for every generator, I draw an arrow like this. Okay. So this is how I could give a proquery presentation. So what I get is a diagram of U instance presentations. Now, I have one entity here. So I have one entity and 2 types. So to that entity, I stick in this instance presentation. And when I stick in a type, I know I have to get representables. And I have 2 morphisms going like that. Okay, so that means that I have a representable, so it has one generator and one generator here. And now morphisms of instance presentations just say that for every generator, I have to send it to a term here. So what I'll do is I'll send n to this term. And that's the term of E's salary plus 50. And then the new name will just be E's name. Okay. Okay, so that's how proquery presentations work. Now, given a proquery, we get a functor, as we saw in Gabriel's talk, and we call this evaluation. So if I have an instance I on V and an object U, then I can get the set on U. And this functor also has a left adjoint, which we call co-evaluation. There's actually a theorem from the algebraic databases paper that says, if I'm a functor between instance categories such that I preserve the type side, type algebras, and it's also a right adjoint functor, then there exists a proquery P such that F is isomorphic to evaluation of that proquery. This is a very nice theorem that we're gonna try and generalize later. So this is what it looks like to evaluate. So this is our V instance I. This is the example we saw before, and now I want to query this data. So I want to transfer this instance from V to U. Okay, and that's what this looks like. So Alice is her own manager, and Charlie is his own manager, and they get a promotion. So Alice's salary is now 150, and Charlie's is whatever his salary was plus 50, because we don't know what his salary was. And this is what that'll look like. And you can do this all on the presentation level. So that's all done already. So let's talk about what we're doing in this new work. So given two proqueries, we can compose them using basically the same thing as profunctor composition, but we have to be a little bit careful here because this is a set and this is an instance on W. Okay, so this is just the tensoring of a set with an instance, and then I take the coend. And this coend is taken in W instances. So this could be a very, very nasty colimit. Pretty much arbitrary as I change the type side. And as Gabriel said, this is very similar to something done in database theory where you compose conjunctive queries. And so I want to tell you a little bit about the history of this idea. So there's these two papers on the algebraic data model. However, what's interesting is that they give two inequivalent notions of proquery presentation. So these are called bimodules in the algebraic databases paper, bimodule presentations, and they're called Uber flowers in the algebraic data instance. To explain, this is select from where it can also be called flower notation, so it's like Uber flower. Anyway, so the point is that in this paper, they come up, they sketch a way of composing Uber flowers, but they never prove it's semantically correct. And then for bimodules, there's no composition given. So this is kind of what motivated us to write presenting profunctors. We were trying to understand this and we realized they weren't equivalent. And that's why this is work in progress, because we stopped working on this to write a whole other paper. So yeah. Now, so it turns out that a semantically correct and finite preserving composition operation cannot be given for bimodule presentation. And that follows directly from what Gabriel talked about. And that was our motivation to write the paper. So our new contribution is to give a fully specified definition of proquery presentation, prove correctness of composition. We also introduce proqueries. So these are similar to proqueries using this analogy: conjunctive queries, unions of conjunctive queries. Here's the formal definition. I'm not going to read it, but it's basically an instance and a proquery, and they have to interact in a certain way. And you also get an evaluation functor. And this just looks like taking the evaluation of the proquery, but you're taking a sum over the set from the instance. So this is what a proquery presentation would look like. So it'd be like, select the name and the salary plus 50 of all the employees who are their own manager, or the name and salary of all the employees in the math department. So I just take this and I union it with this. But notice here that the select clause, the things you're saving them as are the same, but I can choose different terms now when I select. And that's impossible to do with a proquery. With a proquery, you only get one select clause. So here's my old instance. And now when I eval it using this Proquery, I have this and I have this new stuff. And notice Charlie's here twice. Here I've added 50 to his salary, but here I have. So you can do kind of interesting things by combining these different database instances. So as a summary, in the new work, we're going to define a definition of Proquery presentation, semantics, and composition, prove correctness, prove that Proqueries can also equivalently be described as functors between instance categories that preserve type algebras and are parametric right adjoints, also called profunctors. So before we saw that when this is actually a right adjoint, it comes from a proquery. Now we want to say we weaken that to, okay, it's a parametric right adjoint, then it comes from a proquery. And if you don't know what that is, a functor between categories is a parametric right adjoint when C has a terminal object, and when given this factorization that always exists, this functor has a right adjoint. And these have started to show up all over the place in category theory, especially polynomial functors. And that's it.
Thank you.
Thank you. I should also mention that you can go to this website and play around with CQL, the language that Connexus uses for their software, and you can actually like evaluate proqueries using that software. Proqueries are the next thing to be implemented.
Right,
Questions?
any questions?
Didn't really get what co-evaluation was. Going back to that slide.
Yeah, I didn't explain it. Yeah, co-evaluation is just its left adjoint of gamma. But co-evaluation actually turns out to be exactly composition. So I can take a proquery, I can take, yeah, how do I explain? It turns out that you can take a proquery, think of it as UOP to V instances, take lambda of Q, that's a functor from V instances to W instances. And then when I compose those as functors, it turns out to be exactly this. So co-evaluation, you can think of as composition. You can also think of it as certain kind of data migration operations. So I didn't mention the delta sigma pi, which was kind of the old way of thinking about data migration. So co-eval is kind of thinking of it like sigma. And evaluation is kind of like delta and pi. I mean, there's a specific, there's an actual theorem that says how they're related. I won't go into it right now.
Yeah.
At the end, you talk about parametric right adjoints. The notion really reminds me of the notion of polynomial functors or containers, or local right adjoints, but here it's just about the timing object. Is there a deeper connection?
I think that's equivalent, right? Yeah, I'm not 100% sure what you mean by it. I'm pretty sure that's equivalent.
Because in the polynomial, you ask that the induced functor between C and D over F of I need to check again.
Yeah, maybe you don't even need a terminal object. You say for like all objects,
Yes.
something like that. Yeah.
This slices for all objects are maybe the terminal object I don't think so.
Yeah.
Any other questions? Yeah.
So your ability to write unions of conjunctive queries, how does that relate to the duck queries?
That's
That's
disjoint union of conjunctive queries. Yeah. I just like the name better. New proc query. But yeah, it's the same thing.
Yes. Okay, thanks again.